So welcome to Chai and Why. We are, as usual, we are starting at 11. And today it's a great pleasure to introduce Joydeep. Dr. Joydeep Sarkar is a researcher in nanoelectronics group at TIFR. And he works on very fascinating stuff. Something actually starts right from carbon.
Yeah.
Right? And they are able to do a lot of novel work using this. And I may say that they are one of the groups in the world, leading groups in the world in this field. And he has a lot more stories on the science and the background stories of the research as well, I trust.
Yeah.
Apart from doing research, he is also an avid photographer and a musician. So if you have interest in knowing what connects music, photography, and science, maybe you can ask him. He also has a live demos, which since you have braved Mumbai weather and come personally here, so you will get to see. Online audience will not be able to see the demos. So sorry about that.
You can see the video on the screen.
Yeah. So they will see only the video. But whereas you can see, perhaps they can try their handset.
Sure, yeah.
You can also try your handset, this little demos. And with this, it's all yours.
Okay. Thank you, Ullas, for the kind introduction.
I'll tell you one thing. Let it be like there will be a slide. Okay. Yeah.
All right.
Just speak a bit louder because
Sure, yeah.
there is no amplifier here.
Yeah.
So maybe you can sit in front. Like,
yeah. And come on the first row. It will be good. Okay. So let me get started. Good morning, everyone. I'm Joydeep, and I welcome you all to this Chai and Why session. So today I'll talk about graphene, and with graphene, what we do in our lab, mostly that, and we'll try to make it very interactive. So please stop me at any point if something is not clear. So sort of the plan of the talk. So first I'll tell about what is graphene, why it is interesting, and then a bit history of graphene, how people discovered it and what people do with it, and what we are doing at it currently. And this two part here. So I'll talk about what we do in our lab with graphene. We make various quantum devices like an amplifier, a sensor, or even twisted graphene superconductor. And finally, I'll talk about some outlook where you can do more interesting stuff with graphene. Okay. So let us get started. So this is a pencil again. So I hope all of you have used it at some point. And this is made of graphite. So that you can see over here. And microscopically, what is there in this graphite? There are lots of carbon planes stacked together, similar to this. So this is a bunch of paper stacked together. And if you zoom in more, what is there is this carbon layers, and they are one on top of another, and they are stick together by van der Waals force. And this force is very weak, so you can cleave it off, and you can get a single layer of carbon, and that's called a graphene.
Wait. You said we use nanoelectronics.
Yes.
Is that it?
So basically, you go to nanoscale to make now devices and make some electrical devices, electronics out of it. So that's the nano electronics, because we do it at nanoscale. I'll come to that. I have one dedicated slide for it. Yes, so this is the graphene lattice, and this graphene is particularly a family of a material class. It is called a van der Waals material. And there are different creatures in the zoo like graphene, and the advantage here that they are exfoliable. You can go to a single layer for all this material, and they have different properties. Like graphene is a metal, HBN here is a insulator. Also, you can get like a superconductor, a magnet, and different materials. And now, what you can do, you can now put them together and devise some new properties out of them. For example, I can put a superconductor with a magnet and see what happens, or even a superconductor with an insulator and ask question, what can happen now? And this van der Waals material work as a Lego block. So you can stack one of top of another and you can make a heterostructure out of it. And I hope you have seen this Lego blocks at some point, and these are like some building architecture. Using that, you can make any structure you want. So that's the spirit. So this material are used to make any new materials that one wants to do. So graphene is actually called a perfect 2D material. I'll come to that. So this is a graphene lattice. So these are carbon atoms. They are arranged in a hexagonal lattice. And this is called a honeycomb lattice because it looks very similar to honeycomb of honeybees. And if you see here, the thickness of this graphene flake is very small. It's just one atom. So it's 0.3 nanometer. And there are many atoms in the length and the width directions. And if you compare the thickness comparable to the length and width, it's very small. That's why this graphene is called a two-dimensional material. And theoretically, people thought this getting a two-dimensional material is impossible because there are at room temperature always some fluctuations because these atoms, they vibrate, and because of their vibrating motion, this lattice will break apart. So you will never be able to get a single layer of graphene. And that's where these people came. So they first make this graphene just using Scotch tape. So I have also bought Scotch tape here. So you can also use it towards the end. And using this Scotch tape, you can exfoliate graphene just like this. You take one crystal of graphite, you put it here at the middle, and then just peel it off. So this was more like a simple curiosity-driven experiments. They started with a bulk graphite crystal and then peel it to a very thin layer of carbon. And that's they're calling graphene here. And that led to this Nobel Prize 2010 because this graphene is now one of the marvel material that hosts many exotic properties. That will be clear in the next few slides. So how to get this graphene actually? So this is the Scotch tape that I just showed, and you take graphite crystals, place it here at the middle, and then you just peel it off by mechanical exfoliation. And doing so, you can get just one layer carbon, which is here, and this is called graphene. And there are different colors indicating different thicknesses. So typically from the optical image, we can see it, and different color represent different thickness of this graphene material. And once you get this graphene, then you ask, what can I do with it? So then to do anything, what you do, you add wires to it. Like this yellow wires are like probe. Using that, you can send current through this graphene and read voltage and probe its electrical properties. Now, let us try to like understand from our basic atomic physics understanding that this graphene will be electrically conducting or not. So to know that graphene is stable and its atomic number is 6, and it's the electronic configuration. So in the outer shell, graphene has 4 electrons, free electrons. These are valence electrons that participate in conducting electricity. So now if you see the crystal structure of graphene, so this is the lattice of graphene, and here at each site, one carbon atom is sharing 1 electron with one neighboring carbon atom. And this typically, these bonds are called covalent bond. And one carbon is attached to 3 sites. That means graphene had initially 4 free electrons. Now 3 of them are being used. So they can't participate in any electrical conduction, but there is 1 free electron that is kind of delocalized, and it can now participate in electrical conduction. And because of that, graphene can conduct electricity, and graphene is a good conductor. Now there is another material, which is diamond, which is made from also carbon, but diamond is electrically non-conducting. The reason is, if you see the lattice structure of diamond, it's arranged in a tetrahedral lattice, the carbon atoms. So if you see here, now each carbon atom now connected to 4 neighboring carbon atoms, and now all 4 electrons are engaged in making this covalent bond. So there are no free electrons to conduct electricity. So just looking simply here in the atomic arrangement, you can say that the diamond is non-conducting, and that's what exactly it's in practice. So from this slide, we have some understanding that this graphene should conduct electricity. So one simple demo that you can do at your home also. So this is one simple setup. You have a 9-volt battery, 1 LED bulb, and 2 needles. Now what you can do, you can make a line with this pencil, and if that path conducts electricity, then this LED should glow because you are completing the electrical circuit. And that's what I'm going to show you now. So using this pencil, so I've also set up this demo here. So at the end, you'll be able to do it here as well. Can you see that bulb is glowing now? And this is happening just because this graphite is conducting electricity. And now when the line is too large, then the resistance is higher. Less current is flowing in the circuit. That's why you can see the bulb is dimming. And once you are coming closer, it's going brighter. So using this, you can also verify your Ohm's law, like how the resistance scales with length, width, and those sort of things. And lastly, I have put a mark with a pen, ink. So ink uses polymer, which is not conducting electrically. That's why now the bulb is not glowing. Now this is one nice instrument, it's called a multimeter. Using a multimeter, you can probe resistance of different objects. So now we measured the resistance of this line of carbon. This is around 30 kilo ohms. All right, so this simple experiment says that graphite is conductor of electricity. So next, so in the first part, I talked about how you can get graphene and what electrical properties you expect from it. Some simple experiment. Now we'll try to go advanced now and try to see what people have done in the past over these graphene devices and its application. So this is just one image to show the scale of this nanoelectronics world. So you start something like a tennis ball, rice grain, then human hair, a microchip, and finally the graphene device. So typically this human hair diameter is of the order of 100 micrometer. And our graphene chip is a few micron or even nanometers. So you can fully fit the graphene devices in the cross section of human hair. So that's the small length scale that we are going. And there's one advantage. So going to smaller dimension, you can understand the individual properties of this element and now combine them together to make something interesting. So that's the motivation for going to smaller dimension, because there are more control and more possibilities. All right, so the first thing people tried after this graphene discovery is to make a transistor. So a transistor is actually a 3-terminal device, and transistors are used everywhere nowadays in your phone, computer, all digital electronics. So transistors are like switch. So they have 3 electrodes, source, drain, and a gate. And this is one cross-sectional image. So from here, if you see it, so you inject current from this source, and the current goes to the drain. And you have a metallic gate here. And by applying just a voltage at the gate, you can induce carriers in this channel. So this is a channel made from graphene. And when you induce more carriers, the current increases in this channel. So in a way, the response of this device looks something like this. So the y-axis is resistance, x-axis is the voltage. So at 0 voltage, the device shows large resistance. And when you go to positive or negative side in the voltage, you add more carriers in the channel, so the resistance drops down. So this particular device now can be used as a switch. So this low resistance state, you can think it's an on state of the switch. And where the resistance is high, you can think it's an off state of the switch. And this is basically a transistor. It's called a field effect transistor because you apply a electric field at the gate. And these are used, as I said, and many electronics like cell phone, camera, all digital electronics. And now if you compare graphene transistor with silicon transistor, they have many advantages. So in graphene, the electron mobility is very high. The electrons or carriers are very mobile. They can move freely. These are some numbers that graphene mobility is 10 to the power 5, whereas silicon phase 10 to the power 3. So graphene is electron carriers are much mobile in graphene compared to silicon. Also, graphene shows bipolar response. So you can use it for electron and holes, which is not typically possible for silicon phase because they're either N-type or P-type. Also, there are 2 disadvantages because graphene is currently non-scalable because it's flakes we make by exfoliation. So there's a small in size, but there are efforts that people are trying to make large flake graphenes with some modified techniques, and using that you can now make scalable devices. And the fourth point is the on versus off ratio is small. By that mean, I'm saying this ratio of this point versus this point. Since a monolayer graphene doesn't have any band gap, this on versus off ratio is small compared to a silicon-based device because there's an intrinsic band gap in the material. But again, here you can use a bilayer graphene, and there you can, applying a bias, you can open up a gap, and that can now fulfill this criteria as well. So you can get a high on versus off ratio. Okay. So with this, so I introduced you to this electronics part of it. So you can make transistor of using graphene. Now I'll talk about mechanical properties of graphene. It's like elastic properties. So as I said, graphene is just like one layer of carbon. There are single atoms literally. And what will happen if you have a graphene membrane and I put a like heavy mass on this membrane? What did we expect? To tear it? Yes, right? But turns out in graphene, these like in-plane bonds are very strong. They are held together using covalent bonds, and typically the energy cost is very high, 3 to 5 EV at room temperature. So if you convert this to a temperature scale, that will be like 10 to the power 4 Kelvin. So you have to go crazy high temperature to break this bond energetically. So breaking this bond is just impossible. And that's why graphene has very high Young modulus, like even 5 times larger than stainless steel. So what is Young modulus? Young modulus is the material's resistance to stop elastic deformation. So you are trying to break this in-plane bond, and graphene is trying to oppose that. That is a metric here. It's called Young modulus. So graphene is very stiff in-plane, even stiffer than stainless steel. But it is extremely flexible in the out of plane. And because of that, you can make any structure you want. You can curl it up, you can make a cylinder, you can make a wavy pattern out of graphene. And that's the advantage. And since it's like a floppy membrane, you can use it to make mass sensors. I'll come to that. So this is like a musician's drum. We have one membrane here. So you actuate the drum with the stick. And by doing so, you are exciting the resonant mode of the drum. It's vibrating, and different resonant mode will give you different sound. And typically, the resonance frequency is given by the square root K by M. M is the mass of this membrane. So now people literally use this graphene to make drums. So this is one particular experiment from our lab. So we used graphene membrane to make a drum. And since graphene has a very low mass, it's a very good mass sensor. Any tiny object that can sit here on this drum will shift this resonance frequency. And doing so, you can detect the motion or mass of that small particle. And in practice, the mode shape of this drum can be very different or even complex, like here, and that leads to different sound or like different frequencies for this drum. All right, so now I'll show one example here. So mostly now talked about electronic part and some mechanical part. Now I'll try to convince you that this graphene is not only interesting for physicists, but also it's equally interesting for a chemist, a biologist, or even a material scientist. So now here I'm trying to convince you with an experiment where people at Delft University of Technology, they tried to use this graphene drum to sense bacterial motion. Okay. So here in the schematic, you can see these whole structures of the drum. Yeah.
There's few slides for this slide.
Right.
Talked about what is delocalized electron.
Right.
So what actually is delocalized and where the free electron is coming from?
Right. So as I said, like carbon in the outer shell, there are 4 electrons, valence electron, like here. So if you see here, so graphene right here, one carbon atom is attached to 3 neighboring carbon atoms. That means 3 electrons are engaged in making this covalent bond. And you have 1 electron that is free. And that electron is the delocalized electron. And electrons are like clouds. They are kind of delocalized everywhere. And you can have overlap between these electrons. That means electron can hop from one side to another side. And that's how it leads to this flowing of electricity. That's the idea. Right. And that is not there in diamond because all 4 electrons are engaged in making these bonds. That's why diamond is electrically non-conducting. That's the idea. All right, so let me again resume. Right, so we are talking about these graphene drums as a very sensitive probe for bacterial motion. So in this experiment, so they use this graphene drum and they use this particular bacteria called E. coli, and they put that bacteria on this graphene drum. I'll play one video here. So what happens when this bacteria moves, the resonance frequency of the drum shifts, and that you convert to an electrical signal. And from that, you can monitor when the bacteria is very active in motion, when it's not very active in motion. And this one particular control experiment where I'll show this video. So they have this graphene drum, so that you can think that you can see here, and this is the bacteria that's kind of vibrating on top of this drum. So it's moving around and giving rise to this electrical signal in red color. And then what they did controllably, they put an antidote here to kill that bacteria. And when the bacteria just got killed, the response becomes just flat. So by doing so, you can monitor this motion of these nanobacteria and sense it very effectively. So that's why this graphene drum acts as a very good mass sensor. Okay. Now next, I'll talk about another experiment from a chemist like a perspective. And there, they use this graphene transistor to sense gas molecules. So imagine you have different gas molecules, and when they got adsorbed on this graphene surface, because it's just one exposed surface of atoms, and when they got exposed and interact with this graphene flake, what they do, they transfer charges to this graphene flake. And because of that, the resistance of this device increases. And you detect that change in resistance to say that it has adsorbed one gas molecule. And in this particular experiment, they tried different bunch of gas molecules like ammonia, H2O, carbon monoxide, and literally they showed single molecular sensitivity. And now this is cool because this can be used now for explosive sensing. And these are people like exploring more for the security purposes, that you can sense any explosive gas is present somewhere that you can detect using this graphene FETs. All right, so I'll now like show one more example from a biologist point of view and daily life point of view.
Wait, about that bacteria experiment,
right?
What is the minimum mass that one can put?
That's a very good question. So I don't have the number, but I think this will be very small, like microgram, yeah, or even maybe smaller than that. I don't know the exact mass of this bacteria, but in principle, micrograms.
But the dead bacteria will actually be stable.
Sorry?
Dead bacteria will actually.
Right. So what is happening when it's moving, it's changing the resonance line shape. So while it's not moving, so as I said, the graphene drum can like vibrate in different shapes, the top three figures. Now, depending on the motion of this particular bacteria, this mode shape will get perturbed, and that you will see in electrical signal. Right. Actually, there is a liquid medium also. No, so the graphene drum's response first will get stabilized with the liquid itself. And then on top of that, the other like motion of the graphene will now create a net effect. Oh, right, yes. So the liquid won't harm the like properties of graphene. Sorry? Yes. So they use some optical probe to, so what you can do, you can actuate this drum by electrical voltages and start to vibrate. And you see when it's moving using some optical, like optical setup, like you shine laser and you see the reflected laser and change in that. They can precisely monitor the resonance frequency. Okay. So yeah, we are here. So I said this graphene are also useful for chemists because they can be used for sensing gas molecules. And one last example here I'll take. So these are some bioelectronic tattoos. So like nowadays people get tattoos on your skin. And now imagine this will be really cool because this tattoo will not only like make you look cool, but also do something good for you. So these are some stickers that you can put on your hand. And what they are doing, so they can monitor your blood pressure. And people are doing even more for the sensing purposes. So what happens here, so when blood flow through these arteries, they either expand or contract. And that motion leads to a change in the impedance of these bio tattoos. And that you can get or measure by sending current and measuring the voltage across this tattoo. And this is kind of really cool that I found. So I thought this will be interesting to show here. So with that, so I'll just show one last example here, why this is interesting, and then move to our experiments in the lab. So this kind of a big picture overview that this graphene is kind of emerging really as a like marvel material, and you can use it at many sectors for your daily life purposes. All right, so are there any questions? And then I'll like go to our experiments with this twisted graphene and some sensors. Yeah. So good question. So these are not drum. Okay, so the question was, so for this kind of biosensors for sensing blood pressure, are these graphene drums? So these are not drum, but you can think like on your skin, there is a bulging graphene flake, or like that is touching on your skin, just like a sticker. Yeah, sure, definitely, yeah. So these are like removable also. Yeah. Right. 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 So that's a good question. So if you see here, it's not like a very sharp function in graphene. So the resistance change, there's a slow variation here. It's not going to zero directly, but it's glowing gradually. So you can precisely calibrate it. So from the resistance and the voltage, you can exactly say where exactly I am. That's a good question. So for amplification part, we are not saying that we want to use this versus this. So there we'll sit at a particular doping, let's say positive doping, and there use some other trick to get amplification. That's precisely my work in the lab. I'll come to that. So there I'm not saying I want to use this versus this for the on and off. So these are for transistors. For RF amplifiers, right? Yeah. Yeah. Okay. So for RF amplifier, actually, we use some different trick for making the amplifier. So not exactly graphene FET we use for RF amplifiers. Right. Right. So I agree. Yeah. Okay. Okay. I take your point positively. So maybe you can discuss more. But what I want to say here, so for RF amplifiers that I want to talk in the later part, there we park or dope it in the one polarity itself and do some other trick to get the amplification.
So basically, what is asking is, depending on the application,
Yeah.
do researchers have to engineer graphite differently?
Yes. So yeah, so that's kind of modular. Yeah, so that's actually modular. You can do it. You can engineer it. Yes. So the trick is there. You go to a fixed doping. Now you do some engineering to make it a nonlinear element itself for the amplification. Yeah. So you can do that. Yeah.
Basically, I think we'll come to that. What they mean by doping is not essentially some third element being
right. Electrostatic doping.
They are creating vacancies or defects
by applying gate voltage.
Yeah, and that is what graphite is that. So I think we can talk about.
Yeah, I think it will be clear in the last part of the talk, where particularly I talk about RF amplifiers. Okay.
graphite by short shape, how do you place that on the electrode variables?
Very good question. So these flakes are very small, typically in micron scale. That means you can't even see with your bare eyes. So for that, you have to first drop that flake on a substrate and then use electron beams to make some patterns or electrode to it. So by hand actually you can't add any probes to it. So using electron beams, like you have used Rangoli mask, and through that mask you can make any pattern. Similarly, for these nano devices, we use electron beams and use some polymer to make any pattern on it, and then deposit metals to make the contacts. Yeah, maybe I can show in the upcoming part. I have some like devices to show. Yeah.
There are various pencils.
Yeah. How you differentiate them? Yeah. So like simple answer is from the intensity, you can say how conducting they are. The bulb is glowing very like illuminating very brightly, and it's a low resistive. And also you can quantify the resistance using that instrument I call multimeter that can measure resistance of that structure precisely. So for different pencils, I think it will be same because they are all made from graphite, just that their like width of the lead is different for different pencils. But they are all made from graphite, so they will be conducting, all of them. Okay. So, okay, so now I'll move to the next part from our like lab. Okay, sure. So in the next part, now I'll talk about some quantum devices that we can make with this graphene. And that's the fun part that we do in our lab. So first I'll start with this twisted graphene superconductor. So this is one layer of graphene, another layer of graphene. So graphene is now there since 2004 and people thought we are done with graphene. It's just a metal, we exploded enough. There's nothing interesting more. And then in 2018, this idea came up twisting two graphene on top of each other. So naturally in these graphite crystals, these graphene flakes are just placed on top of each other. There's no relative angle between them. And this particular thing is called the engineering. And in here, what they are doing, they are placing one layer on top of another layer with a relative twist. And doing so, this system can become a superconductor. So your original single flake was a boring metal. Now this composite system can become a superconductor, insulator, or even a magnet. And how you do that? So I'll play one video here. So here you are changing the angle. Can you see some patterns here like flowers? And depending on the angle, these flowers are then either coming together or going apart. So this is called a Moire pattern. So it's very similar to beating of sound. So when you have two sound waves of similar frequency, they beat with each other as if they interfere. Here similarly, two like lattice structure, they are similar in like all aspect, and they are interfering with each other and giving rise to this beating pattern. This is called a Moire lattice. This is called a artificial lattice. And here, doing this twist, you can now make this system becoming a superconductor. All right, so there was one question from the YouTube, how you make these devices. And so this is how we make it in lab, these devices. So this is our graphene flake. Use a very sharp needle to cut it in two pieces. And then we use one substrate to pick one layer first, as you can see here, then rotate the other flake at some angle theta, then pick it up again and drop on another substrate. So now this graphene flake is kind of sandwiched between two substrate, and this substrate we call a hexagonal boron nitride that is used to encapsulate and chemically protect it so that there is more mobility in the graphene. Here is one. Oh, sorry, maybe you can come a bit in front, that will be easier.
Also, perhaps you should go this part please.
Slowly, okay? Okay.
Sit in front. But you just want to go further away. Please come in front.
Yeah, on the first row you can sit. So as I said, you need two layers of graphene. So actually you can't take two random flakes and twist them together. You have to use one single flake because it's a mother flake. You cut it in two parts so that you know precisely their crystallographic axes are, and then put the relative twist between them. So that's what we are doing here. So this graphene flake, using a tip, we cut it into two pieces. Then using a sticky polymer, we pick them up. So the first graphene got picked up. We rotate the other flake and then picked it up again and then drop on a substrate. And then what we do, we put a polymer resist on top of this graphene and make these structures using electron beams. So these are very similar to Rangoli mask. We have a mask. What you can do, you can put colors to that mask, and whatever structure or pattern in that mask is, that will come on your floor or yeah. And this is the optical image of our device. So there are many electrodes connected to it, and these are made using the same technique of electron beam lithography. And this particular structure is called a Hall bar geometry. And as you can see here, there are many probes. So these are for sending current and measuring voltage. So you can send a current from probe 1 to 2 and measure the voltage between 3 and 4. Or also you can measure the voltage between 4 and 6. And why we put different probes here? Because we want to probe the different region of the device, how it behaves, which part is superconducting, because the device can have some spatial inhomogeneity because these are very thin atomic layer, and when you twist them, what can happen? Some part can curl up, right? And because of that, whatever angle you put at the first place may not be the same angle at the other place. There can be some variation. And now to probe the whole device, we make many connectors and probe them individually. Okay, so this one slide, this slide become a bit technical. Yeah.
You are basically preparing graphene as per your experimental advice.
Right.
Like in the line of the questions what was asking.
Yeah.
Or sensor application or what application. You have to prepare graphene in advance.
Right. Application, yeah.
Then you are doing like this to make necessary electrical product.
Yeah. So we start from scratch. We take a scotch tape. What are the basic gates, logic gates? I think in principle you can apply any gates for graphene transistor that you can apply for other transistor.
Actually, there are really building logic gates in that. It's just transistor as a switch.
You can show it here.
From panels from digital electronics. So the technology is not yet advanced enough to build complete logic gate. It's not that. They are experimental setup using just probably one or two devices like that. Not fully functional logic.
Yes. So I started with one crystal here. I peeled it off in two parts. Now you can repeat this many times.
So this is what basically.
Yes, same thing. Yeah, that's how they discovered the graphene and got the Nobel Prize. As you can see, it has thinned down quite a bit now. And if you put this on a substrate now, silicon substrate, there's a probability you will get a single monolayer of carbon. That's the graphene. Yeah.
That graphene can work.
Yeah.
What exactly is how exactly is graphene of required?
Right.
Introduce effects in a certain programming.
Yes.
How does that? That's what you're
Yeah. Right. So first you get the graphene flake, and then this electrodes that is kind of customized. Based on your requirement, you can put different electrodes. For RF devices, we just need 3 electrodes: source, drain, and a gate. I'll show that. For DC sort of application, you want to probe different regions of this graphene, then you can add many probes here. So based on your requirement, you can change the design of your electrodes on this graphene plate. There will be any? Hindrance. Oh, that's a good question. So what? Yeah. So what can? So the question is, when you twist to graphene, can there be some sort of hindrance? Actually, it can happen and curl up some, because it's a very thin membrane, right? And when you put one top of another and twist, there can be imperfection in the twist, and some part can get curled up. And because of that, the angle you initially dialed may not be same everywhere. Some part will have different angle, and that part may not become superconducting. Because this thing to become a superconductor, you need a particular angle called a magic angle of 1.1 degree. And if you can hit that angle with some error bar plus minus 0.1 degree, you can get the superconductivity. So spatially, the different part of the device can have different response. So yeah, that's sort of
so what I suggest this material processing questions, let's save these questions for the later.
Yeah.
Proceed with the talk, and then you can probably ask after the break.
Yeah, we'll come to that question. Okay, so very briefly here. So what is happening here? What causes the superconductivity in a twisted graphene? So you can think in monolayer graphene, single layer graphene, the electrons are like very free particle. They are moving very fast. They are not talking to each other. They don't care what other electrons are doing. And when you twist them on top of another, what it leads to something called a flat band. And what happens here? The electron's velocity becomes very slow. Now consider there are many, many electrons, and they are now interacting with together. And they are now collaborating to make something funny. And that's the superconductivity part here. The enhanced interaction between electrons now gives rise to some new phenomena like superconductivity, magnetism, or some insulating behavior that is not observed in single layer graphene, where electrons are mostly free. They are kind of single, like they are moving alone, not talking to each other much. So this one result from MIT. So they first observed this experimentally, this twisted graphene superconductor. So what they did, as I said, they rotated two graphene at 1.1 degree, and then they cooled their sample to low temperature. And what they found, so that here there are two graphs here. The image is the image of their device. The x-axis is temperature, the y-axis is resistance. And when you decrease the temperature below a certain temperature called a critical temperature, the sample becomes superconducting. The resistance goes to 0. That's what happened with the superconductor. And it's kind of interesting because it's called a phase diagram. So here in the color, what I'm showing is the resistance of the sample. Red mean very high resistance, blue mean low resistance. And exactly at this dark blue part, the resistance is 0. The sample is superconducting. And in the x-axis is doping, and the y-axis is temperature. So here to here, you are decreasing the temperature. Here to here, you are increasing electron doping. You are putting more electrons when you are going from left to right in the x-axis. And doing so, you can tune this carrier density or doping and temperature. And doing so, you can convert this sample from a boring insulator or metal to a superconductor. And that was the fun part here. And there is even more, that you can get also magnetism in these systems, where single layer graphene doesn't show any of these properties. It's not superconductor, not a magnet, not an insulator also. And that's the fun part here. Okay, so any question from here? Otherwise, I'll move to the next part, which is this quantum sensor based on graphene. Right, so these are called electron-electron interactions. If you know about superconductor, what they do, so their electrons, they glue together with some phononic interaction and make something called a Cooper pair. In Cooper pair, there are two electrons held together with some interaction, and they carry this supercurrent with 0 resistance. So in graphene also, it's like electron-electron interaction that leads to this formation of superconductivity. Okay. Right. Yeah. Right. So this is actually in your hand. That's the fun part here. So typically for like 3D metal, what we do, we every time dope it and make a new metal with new concentration of doping. But in these 2D devices like graphene, you can add a voltage and just change this carrier density continuously from one value to another value. So in their experiment, what they did, they are sitting at room temperature, changing electrical voltages from some knob, and that's changing this carrier density here. So that's why it's interesting, because just changing a knob, you can make one device from an insulator to a superconductor, or from a metal to a superconductor. So yes, like for transistors, so the way graphene first was discovered, it was a semiconductor, a semi-metal. People made transistors out of it. Now, when the time progressed, now people are exploring more aspect of it. So can you make something new? And that's where the superconductivity aspects comes in. Now, in the next part, I'll talk something else. It's called a Josephson junction. It's a superconducting field effect transistor. It's like a transistor, but with zero resistance. Okay.
What about that? And over the period of time, you have to find newer aspects of graphene. Like this, what is just superconductivity. The superconductivity in crystal graphene was discovered almost 50 years after graphene was first made.
Right. Yeah.
So, as science is advancing and as people are learning more and more about graphene, they are doing more experiments, making more theoretical predictions, and graphene is growing even more wonderful.
Yeah. That's the beauty. Actually, in a single material, you can get a lot of different properties. That's simply not possible with any other material in this world.
For example, 1.1 degree, we just said 90 angle. I think if you make 2 degrees instead of 1 degree, you won't see superconductivity.
Right, right. So there's some like very spatial interaction happening. So what happens actually, there are two layers, and the electrons on the top layer and bottom layer, they talk to each other at this particular angle and they hybridize. That's where the interaction comes in, this electron-electron interaction. They can now hop from the top layer to the bottom layer easily. There are?
Just compared with
Oh, yeah. So you can also have electron on hole. It's a bipolar device. So in the positive gate voltage, you are injecting electrons. In the negative gate voltage, you are removing an electron or you are injecting a hole. It's bipolar. Unlike semiconductor, typically semiconductors are either n-doped or p-doped. Okay. All right. So the next part will be fun. So now we are trying to make something quantum using graphene. Okay. So a few basic slides to kind of introduce you to this quantum world. So consider you have a ball and this barrier. So in classical, if you think, this ball can't really go from here to here without escaping this barrier. It has to go from the top of this barrier to go on the other side. Wherever in quantum mechanics, we consider particle also as waves. Okay. And because of that, now this can penetrate to this barrier and can go on the other side. And then the question is, where can I see this quantum phenomena? How big object can I take, and where I can see this quantum phenomena of tunneling and all? And this one cartoon to show that this, you know, this idea of Schrodinger cat. So now there's a big cat, like a lion sitting on the other side. You are feeling safe classically because there's a wall in between. Now in quantum world, what can happen? This lion can penetrate from this barrier and can chase you. That's the fun part of this quantum world where, sorry? Yes, so that's the idea. So things behave a bit weirdly here. Particle can also be like an wave, and they can penetrate through. So consider a like very energetic wave, like gamma rays or X-ray, that can penetrate through a plate, right, easily. You consider a football, you kick it, you can't really go through a glass. You take a bullet, you can pass through a glass. So it depends on the energy and what is associated with it. So a particle can also behave as a wave in quantum mechanics. Right, exactly. Yes. And the rationale for showing this image is, now the idea is at what big objects or till what big objects you can observe this quantum phenomena. Okay. And that's precisely the Nobel Prize last year these three gentlemen, they showed that this quantum phenomena can be observed in even electrical circuit as big as like few micron chip. Yes, right, through a barrier. A particle can pass through a barrier, which is classically impossible, but in quantum mechanics, it's possible. Okay? Yes, because they behave as waves, and wave can penetrate. In quantum mechanics, particle behave both as particle and wave. Yeah. Okay, so, and they used one idea, which is called one element is called a Josephson junction. So what is Josephson junction? I'll take some moment and explain it like from here. So Josephson junctions are made from superconductor. And we just discussed superconductors are element where the resistance is 0. Their charge can flow without any dissipation. So they have 0 resistance. And then Brian Josephson came up with this idea. What happens when you put two superconductors very close to each other and there's one barrier in between? So now this is the barrier that is showed in that schematic. So this is one object, this is another object, and there is one barrier. So classically, we will think whatever carrier is here, you can't really send from here to here. And in quantum world, what can happen? This particle can go from one side to the another side and can give you a current, a dissipation-less current. And this phenomenon is called a quantum tunneling. And because of this device, so Josephson got this Nobel Prize in 1973. It's called a Josephson junction. And in this device, you connect to superconductor by a weak link. And because of some phase difference across this weak link, a dissipation-less current can flow from one part to the another part. And here, what you are tunneling actually called a Cooper pair. It's a pair of two electrons with opposite spins. Right. So good question. So in quantum mechanics, we everything described in terms of wave function. And that wave function, it's like a complex function, can have a amplitude, can have a phase. Now here, my two blocks are quantum mechanical. So this block has a wave function of this form, psi some square root n e to the power I phi. The other block also has a wave function, psi some square root n e to the power I phi. And this phi is the phase called condensate wave phase. Be technical, but this is the phase of the superconductor. And since the phase is varying across this barrier, the current can flow. This is very similar to a potential difference across a battery when you apply a battery. This is like a phase battery, you can call it. Yes. So, yeah, right. So that's the idea. So if you have equal potential everywhere, will you get a current? No, right? Your one lead has to be at a higher potential than the other. Similarly, it's called a phase battery. You can think as a phase battery. One part has a higher phase compared to the other one. So they have a phase difference. And because of that phase difference, current can go from one part to the another part. Constant amplitude, yes. If they're identical superconductor, they have constant carrier density, so the amplitude is constant. Yeah. Right. So here is the phase is different. Yes. So you can think it as a phase battery. And because of this phase difference, current can flow. Okay. And these are very interesting elements, Josephson junction. So these are like inductors. So in electromagnetism, we have seen this coil. And when you pass a current through it, it has an inductance associated with it. And what this inductance does, when you change this current as a function of time, it opposes that change, right? So similarly, this Josephson junction acts as an inductor, but it's a nonlinear inductor. And how do I mean by nonlinear inductor? Now consider this simple spring mass system. The spring is oscillating with some amplitude. And if the spring constant is linear, like just a constant, then it will have simple harmonic motion. But if somehow I can make this spring constant also a function of position x, this can become a nonlinear oscillator where the resonance frequency will depend on this k function of x. And if you can change the stiffness of the spring, the resonance frequency will also got changed. This is what called a nonlinear oscillator. And these are used for making amplifiers. I'll come to that, how we make amplifier using these Josephson junctions. All right, so as I said, these are very interesting because nowadays, this Josephson junction build the building block of your quantum technology. So they are used in superconducting qubits, amplifiers. They are used in metrology to define the unit of voltage. What is precisely 1 volt? And then now recent years, people are using this for quantum sensing of radiation, electromagnetic radiation, and some exotic particle like dark matter. Okay. Right. So this is a quick recap. Why do we need amplification? It's very classical analog. So consider you are moving in a crowded road. Your friend has left behind and he's trying to communicate with you. He's shouting, but you are unable to listen them. Now, precisely what can they do? They use a microphone and they can say something and you can hear it easily. And this is the need for amplification. In a noisier environment, you want your signal to raise above the background noise. Okay. And right. So where these amplifiers are used that I'm going to talk about. So they are used in quantum experiments. So quantum experiments are done at very low temperature, typically at 10s of millikelvin in a very cold environment. And these are quantum state. So they have this energy level 0 and 1. This is the ground state and first energy state. And this is a qubit. And this qubit, whatever signal they give, they're very small in amplitude. And if you want to process that signal at room temperature, that signal will be buried below the noise floor of your instrument itself, which are at room temperature. That's why you need this amplification in between, because your electronics at 300 Kelvin at room temperature, and these experiments are done at 10 millikelvin. So there's a huge temperature gap. And because of the thermal fluctuation, your actual signal that's coming from this qubit can get suppressed. So in practice, actually, there are like chain of amplifiers that are used. And the first amplifier is very important because it amplifies your signal, but also adds some bit of noise. And any amplifier you pick from anywhere, they'll always add some noise. Like if you pick some amplifier based on transistor, they are resistive elements, so they have some Johnson noise at a particular temperature, T. And now we are trying to make this first amplifier using a superconductor. So they have zero resistance. They don't have any resistive fluctuation or temperature fluctuation, but they have something called quantum noise, and that comes from the laws of quantum physics. Okay, so you want in this amplification chain, the first amplifier to be as good as possible, very low noise amplifier. And these amplifiers are called parametric amplifiers. And this one example I'm taking to explain you what is parametric resonance. So consider you are like moving on a swing, and I don't know if you have experienced ever. So if you can modulate your center of mass up and down, you can increase the amplitude of your oscillation. So here I have one small video to show. So this person is swinging here, but while he is going away, he is going up and down. And by doing so, he is pumping energy into the system and getting an amplification. And if you want to understand on a circuit level what is happening here, you have one signal of this frequency. You want to amplify it. So you borrow power or energy from another signal. It's called a pump. And then you try let them interact. So energy can now come from this pump to the signal, and signal can amplify. And doing so, you can amplify your signal. And this is nothing but just a conservation of energy. So you want to amplify some signal of some particular frequency or energy. You take energy from another signal and amplify it. All right. So now coming here. So this is one device that we made in our lab. It's called a parametric amplifier. So this is a silicon chip. The device is sitting here, and this wire that you are seeing, these are very thin aluminum wires, like comparable to your like hair diameter, and those are making this electrical connection to this chip. And if you zoom in here, this is an optical image of our device. So this is a graphene-based Josephson junction. So here our graphene flake is. These two fingers that you are seeing, these are two superconductors, and combinedly this part makes the Josephson junction. And this is a capacitor. So combining capacitor and Josephson junction, which is an inductor, you make a LC resonator. So this is the circuit model of our device. So it's a parallel LC resonator with a resonance frequency 1 by square root LC. So the L comes from the Josephson junction and C comes from this parallel plate capacitor. Okay, so after making this device, what we do, we cool them in our dilution fridge. So this is a dilution fridge. I hope you have seen in many this quantum posters or quantum blogs. So this is a dilution fridge. The base plate here goes to 10 millikelvin, and the top plate is at room temperature, 300 Kelvin. Then this is at 70 Kelvin. This is at 4 Kelvin. This is at 700 millikelvin, 100 millikelvin, and 10 millikelvin. And we put our device there, and how I want to explain to you how the amplification comes here. So as I said, these are non-linear device. And when you probe them, what you do? You drive it and you see what is the changing in the amplitude. So this is the oscillation amplitude of a nonlinear oscillator as a function of frequency. And these different colors represent different drives. So this blue curve is at very low drive. You are driving it very slow. So it's like a linear resonator. You are increasing the drive, it is increasing the amplitude. But because of the non-linearity, now what happens? This line shape becomes very asymmetric. And if you consider this point as your resonance frequency, the peak of this curve, that shifts. And this is the kind of smoking gun evidence of a nonlinear system. Yes. Because of the nonlinearity, the resonance frequency shifts. And even fun thing is, at some particular drive, it becomes multi-valued function. So if you consider your frequency here, you have one solution here, you have one solution here, you have one solution here. So experimentally, the system becomes very kind of unstable there. So this is the perfect bias condition of your device. There, the response is very sharp. As you can see in this yellow graph, the response becomes very sharp, and any small change in the signal now will get amplified here. And that's the key part for this amplification. Yes. So now for this device is kind of doped in a particular state, like n-doped or electron doped. And the amplification comes from the fact that this is a nonlinear system. And by changing the drive, you can make it very sharp, the resonance. And right at this yellow curve, you can get the amplification. Right, I hope this clears your question. Right. We can talk more. Yeah, so not very narrow band. So what you are seeing here, a very sharp line. In practice, it can have some width. It's kind of a slanted line. It can have a width. Yes, there's a gradient, and that's the bandwidth of the amplifier. You can change your bias point across that. I'll show that data right here. So this is the data from our parametric amplifier. So it shows good gain around 20 dB, which is like 100x in power, 100x power amplifier in RF frequencies. So yeah, and the bandwidth is 10 megahertz. So as you can see here, the gain is kind of varying from here. Sorry, the gain is kind of pretty high here, like above 20 dB in this 10 megahertz bandwidth. It has a finite bandwidth. And you can tune the resonance frequency of it. So over 3.5 gigahertz, and it has very low noise. So often this noise is quantified in terms of a temperature unit. And the noise temperature of our device is 250 millikelvin. And the best transistor-based amplifier is called a HEMT amplifier, made using gallium nitride. They typically have noise temperature of few kelvins, 4 Kelvin, 5 Kelvin. And this is one magnitude lower than that. So these are very low noise amplifier. Okay, so with that, I hope I address these parts, the first 4 that I promised to tell. And in the last part, now I'll talk about what next, what you can do more with this amplifier. And this is kind of really interesting. So here, lots of interesting phenomena happening in this energy scale of gigahertz, both for this like astroparticle physics and like a material scientist point of view. So in astro, there are many effects like this cosmic infrared background. From this particle physics, we have this dark dark matters. Yeah, you have this dark matter. They have typical energy in this gigahertz, and these are very low energy. So these are very hard to detect. And that's where our devices can be helpful. So upon shining energy here, so what can happen? The response of the device can change, and you can see a shift in the resonance frequency. That's shown here in this graph. This blue versus red curve. You shine some energy, and then the resonance frequency shift, and that you can accurately pick up using this graphene-based amplifiers. Okay, so with that, I hope whatever I promised, I was able to tell you about that, and I acknowledge my lab people. So our lab is at TIFR, which is in Kolaba, Mumbai. And if you want to know more about our work, you can check our webpage. This is tifr.res nano. And yeah, we also host public events in TIFR. Like annually, there are 2 events in February and November. And if you are interested to visit these things, like in person in lab, I invite you to visit our lab and see this. Yeah. So the last data that I showed here, so this is done at TIFR. Yeah, so we made it from scratch, we characterized it, and then made something even like more interesting, like a sensor. An amplifier is now also behaving as a good sensor.
Basically, what they currently do, we can discuss after the tea break. So what we do is we'll take a few online questions, stop the live stream part, and take a and then you can ask all the questions. And I think you can ask a lot more about what they do, and he has even more to tell you about what they do.
Yeah.
Okay. So this one's question is, when you say that you are exfoliating graphite and make graphene,
Yeah.
how do you actually make connections? That's one question.
Okay, I'll go to that slide, maybe that will be helpful.
Question is, how do you place electrodes on?
Right. So if you can see this screen, so this is our graphene flake. So we do this causative exfoliation. We get the graphene flake on a silicon substrate. Then what we do electron beam lithography. By using electron beams, we make some patterns. And these patterns are here, these yellow colored probes. And using that probe, you can send current and measure voltage. And this is not like the full picture. So this is on a chip level. And then if you zoom out more, what you will see, sorry. So this is how the device look like. So this is a silicon chip, the scale value is 2 mm, and the device is here. And if you zoom in more here, now you can see this zoomed image, and the graphene is even hidden inside. So at this small dimension, this is typically 20 micron or 10 micron length scale. So they are very small, so you have to use fine electron beams to make the connections.
So I think this question of how do you guys actually place a contact is somewhat, everyone has this question.
Yeah.
How you make contact? How do you know that your contact is good contact?
Yeah. So
let's discuss that. So we'll take 1 or 2 more questions. So the next question is about large scale manufacturing of graphene. So this peeling will probably be
right.
Very small.
Small flakes, yeah.
Also, you don't know by peeling whether your 2 flakes are similar.
Right.
So is there any progress on making graphene at industrial scale?
Yes, there is. People are trying different technique. One is like very famous. It's called chemical vapor deposition. And doing so, you can now grow graphene flake on a 4-inch wafer, and that can be used to scale up the devices. So earlier, when people found this graphene flake, that was more like a curiosity-driven experiment. They do this scotch tape exfoliation, and they got typical small flakes, few micron. And if you want to like translate this to a real-world technology, you have to have scalable architecture. And for that, people are exploring different growth techniques like CVD, and from there you can get large flakes, like a full wafer flake.
Okay, so I think online we have covered all the questions. So if you could stop the slide share for a moment,
Okay.
We can announce the upcoming sessions and then stop the online. Okay, so let's thank Joydeep for a nice talk.
I hope it was clear.
I can only tell you that since we work in the same building, that there's a lot of toil, a lot of patience required in all these works, and it's certainly not as simple and as straightforward as he described it.
So actually, I got one device that we show that I show in the screen. So I can pass it here. Okay.
So what we'll do is like let me tell you about the next session. The upcoming session will be on 2nd of August at Prithvi Theatre. It will be a talk on biology. This is titled "Evolve to Understand Evolution." It will be given by Amitesh Anand. 1 month from now, that is the third Sunday of August session will happen at Nehru Science Museum, not here. Okay, so just please remember the change in venue. And India will celebrate Space Week. That week is basically India's Space Week. So Professor Mayank Vayega will give a talk on India's space explorations and going beyond the Earth. That will be on third Sunday of August. So yeah, that will happen at Nehru Science Museum. Nehru Science Museum, not here. August 3rd Sunday will not be at Rupali. Yeah, so we'll tell you all that. We'll tell you all that. So it's high time we thank Rupali College for giving us this nice venue, and also thank again Joydeep for a talk.
Yeah, it's my pleasure.
Stop the online part. You guys can have tea. Online audience, as usual, please make your own tea. And after tea, you can ask all your questions to the speaker.
Yeah. So I'll pass one device that I just bought to show you all. So this is that low noise amplifier. This is how it looks. So there are many bonds that you can see, very small bonds. There's a silicon chip, and then there is a graphene device at the middle. The bonds are aluminum wires. Here, you can pass it around.
So, yeah. So the tea is here.